Hello guys, welcome back to the computer organization and programming class. So we start covering floating point unit and the microprocessor. So let me see, just to remind you what we covered in the last class. So in the last class, we learned how to represent real numbers, right, using x86 system. And we learned the big picture of how to convert or how to store a binary number using the IEEE system. And I hope that was very clear in your mind. So now we know how real numbers as a data is being stored in the system using the x86. And we also looked at how the FPU, the floating point unit, works in terms of processing real numbers. Okay, so we know that the from the last class. Let me see if I can get you back to the big picture right here. So this is what we said. We just covered the integer unit right there, the ones that we have right here. And then today, in the last class and today, we're gonna focus mainly on the real number unit or the floating point unit. Okay? So in this part, we will learn how real numbers are stored inside the microprocessor and what type of registers and how to access those registers. And we're gonna go into the arithmetic operation like add, sub, and so on and so forth. So one thing that I just need to remind you with that the floating point is completely different from what we already covered right now. So we spend the entire almost semester, okay, it's like mainly 80% of the time learning the integers. And then we start just now covering the real points. Okay, so the floating points or the real numbers, that's what we covered in the last class. They are actually stored on registers R0 to R7. This is similar to what you guys know in the ARM architecture. Okay, and the size here is going to be an 80-bit. That's what we learned in the last class. And again, I just want to remind you that those registers are no longer used with the floating point, right? With the floating point system, because it has its own registers. And one thing that we learned last time, we don't really, in the integer arithmetic, we're just gonna say add, right? That's what we learned to EAX maybe 1, right? So that's what we did in the integer unit. And the floating point, you're not gonna say fadd because we are gonna use a different instruction. We are not gonna say R71 because we are not gonna use the names to access them. So it's completely different from the integer unit. Okay, so the floating point unit is completely different. All right, that's what I want you to keep in mind. And remember, the microprocessor is divided in 2 units, the integer and the floating. So forget about what you learned in there. I mean, in terms of floating point, when I say forget, you need to relate what's really similar, but if it's different, then you have to accept the architecture. Okay, so the way we access the registers right here is we are using the ST. Okay, so we have from ST to ST0. And we know the ST0 to ST7. And we know the ST0 is always pointing at the top of the stack, regardless. So in this example, the top of the class of the stack is R3. We don't know what is the next top of the stack, okay? So this is the basic idea. So these are the registers, and the way you access them is through the ST0s, okay? I will show you that in the on the Visual Studio, all right? And we know that this is the basic idea. We also learned that we need to load or store data. So when we load, we are getting things from memory to registers. So we have specific instruction. And when we get it back from the stack to the memory, we have a store instruction. We don't do that in the integer, right? Because in the integer, we just say move from EAX to memory 1. So we are moving memory 1 to EAX. Or we're going to say move to memory 1, the content of EAX. So we're just using the same instruction. Here it's different. We have different instructions for different purpose, okay? And this is what we covered in the last class. And then we learned one thing, that the floating point unit works on the postfix. Okay, so the postfix, if you give this expression right here, it's data first and then operation. Data first and then operation. And that's what we learned in the last time. So you need to keep that in mind, the postfix. And these are some examples right here. The very complex example, which is this one right here. So you can see data always first. Push the data because it's a stack architecture. If it's a stack architecture, then we have to push, and then call the ALU. So the ALU is going to assume that whatever you need to operate is a binary. Most of the time, it's a binary operation. Okay, so if it's a binary operation, the ALU is going to assume that the data is in the top of the stack. Okay, so you need to push A and B and call ALU. And then you push C because now you have a result in the top of the stack. Okay, then now what we need to do, we need to push C. So this is now the new top of the stack, which is the C, right? And then we're going to do the operation, right, which is the division right here. And then we're going to push E and F, and then we're going to do the operation. And whatever the operation we're going to get, this is the last operation. So the data we get out of this operation and the data we get out of this operation, these are now the top of the stack. Then now we're going to call the multiplication. So this is what we covered in the last class. And this is also the example that I covered step by step. So just keep your eye on this example, okay, in case if you are confused. And this is what we need to cover today. So we're going to start learning what's push and how the push works. Okay, so the push is always going to do what? Decrement. All right, and this is true for the integer unit as well, right, guys? So we're going to decrement the top by 1. So that's the top of the stack. And here, the top of the stack is what? 3. I don't care about the register name, right? Right here, all I care about is ST0. But we know the top of the stack is 3 because it points at the register 3, right? Register number 3. So that's 3 right here. If we subtract 1, then we're going to get to register 2. Okay, so the pushing starts from the top, 7, 6, 5, and is going to go to the R0. And we will see what happens if we reach the R0. We don't have any way to go further, right? So what should we do? All right. So if we go to this part, then first it decrements and then it's going to copy. Okay, so if there is a value right here, we first decrement. So we're going to point at this space. That's going to be R2 is going to come here, and then we're going to copy the data in there. I will show you an example, okay? But this is what you need to keep in mind. If the top equals to the 0, so if we reach this point and we need to decrement, so there is no place to go, right? If that is the case, it's automatically going to wraps around to the register 7. So it's going to go back to the top again. And when that happens, if there is a value in here and you're going to push or copy the value right here, you're going to see an error message. Okay? If this space is unoccupied, then it's okay. You can store the value right there. Okay, guys? So this is pop. Pop is the other way around. So you want to copy from the stack to the memory, right? Or from a register to another register, right? So you first copy the value and then you change the top because the top is no longer what? It's no longer R3. We copy the content in R3 and then we're gonna what? We're gonna add. So the next value is gonna be what? It's gonna be R4. Is that kind of clear? So that's gonna be the top of the stack. That's the top of the stack. And if we keep adding and we reach R7 right here, there is no further space to go, right? So that is when that's when the CPU is gonna go and wrap it to what? To the R0 and start the process again. Okay, so that's the basic idea. So if you look at the example right here, remember, we decrement and then we copy. Okay, so if we are right here and we have this value and we need to push, so this is pushing 1 and maybe 2, right? So if we do this one, this is going to be the first push. So it's going to decrement and push this value, right? So this is the state right here. And if we want to push the second value right here, then we need to decrement. So this is the top of the stack now. And then we're going to push the second value. Do you see it? So it's going to go like this until we get to the R0. And if we are full, then we have to wrap it back to R7. And again, we have to make sure that there is no data in R7, okay? So this is the idea of the pushing the value, okay? And the same applies for copying the value, okay? So we have different way when we're talking about floating points. You cannot help but you look at rounding. So I'm not gonna cover rounding in details because we just wanna focus on the big picture right here. But definitely you have maybe looked at the rounding in the data structure or introduction to programming. You might have seen different type of rounding algorithms. And when you take the introduction to algorithms, they will talk about different algorithms that can handle rounding problems and floating point systems. Okay, but I will introduce you to a simple idea right here. If floating point attempts to round a number. So the one technique that you can use right here is this technique, right? So you're just gonna add, okay? So you can do rounding by adding, okay? So if you add 1 to this number right here, that means you only need to round to 3 digits because of the limitation of the hardware, right? So if we want to do this, then we're just going to add 1 to this number. So if we add 1 to this number, right? So this is 1 and a 1, 0 and a 1, right? 1 and a 1, 0 and a 1, 1 and a 1, 0 and a 1. And this is going to be what? 1, right? 0.1. So it's going to be 1.100, and this one is going to be rounded, this 0. So this one is already being rounded. Okay? So you can do it by addition, or you can do it by subtraction. Or there are, in fact, many ways, many other ways to do the rounding. Okay, so the x86 supports all of these rounding algorithms. Okay, and by default is going to go by the basic rounding algorithm, which is by addition. All right, so I'm going to move into the other part of the FPU that you need to focus on, which is exception. So now we know rounding. The basic rounding is just going to be by adding. And the exception, what if something wrong happened? Okay, so these are the things, these are the exceptions that gonna automatically be captured or they're gonna be, or they will be captured by the CPU automatically. Okay, so like invalid operation or divide by 0. Okay, and if any of those things happens, there is a mask bit. Okay, so there's a mask bit inside. It's like the E flag, if you remember, in x86. Okay, so if this mask bit is set when an exception occurs, the exception is handled what? Automatically. That means the FPU is it knows this exception. If it's clear, then software exception handler is invoked. So you have to handle the exception yourself, okay? Because the FPU cannot handle this exception. It's beyond what x86 or Intel provided for or programmed or provided a hardware support for, okay? So this is basically part of the FPU, all right? So the focus is mainly on this part and in the instructions, but these are things just for troubleshooting. If it happens that you go through a problem, then you just need to understand whether the exception is known or unknown, okay? And the rounding algorithms as well. All right, so right now we're gonna go and look at the instructions. So what we have covered right now, the basic instruction like sub and add and and I, mul, right? And mul and dev and idev, right? So these are all for integer unit, CPU unit, okay? So now when we deal with the FPU, all instructions, they're gonna start with an F. You see it here? So that shows that this F add. So the CPU will know that this operation code is different from this operation code. So the CPU will recognize that, oh, I need to go to the floating point unit inside the CPU because that's a completely unit by itself, okay? So these are the ones right here. So that if you see the F, then you immediately know that this is not the mul for the integers, all right? So this is something that you need to keep in mind, okay? And the second letter also is gonna identify the data type, which is very interesting right here. Okay, so this is maybe deals with the binary. This is maybe here, it is gonna deal with the stack, right? So maybe the second or the third letter is gonna identify the type of the data that you need to handle, all right? For some of the instructions, not all of them. But what I want you to keep in mind that the floating point is all distinguished by the F instruction, the F letter. Okay, and this is a key point. If you understand this, then you can handle any type of errors you might encounter when you start writing your own code, okay? So first is that some instructions, like you're gonna say F add, and you provide no operands. So this is the 0 operand. And sometimes you're gonna say F add, and you're gonna say maybe ST0. So this is 1 operand. And maybe you're gonna say F add, and you're gonna say ST0 and ST1 maybe, or 3 or whatever. Okay, so this is 2 operands. So these are the type of operation that you need to handle. But you need to keep in mind that the floating point, no immediate operands is going to be provided. So if you have an immediate, you have to store it first in the stack, and then you're going to access it after that. Okay, so this is very important, okay? And you cannot use the general purpose register. So if you have a data on EAX or an EBX, you cannot use it, all right? So you have to convert it into a floating point or store it by storing it inside the stack, okay? And if you have an integer, we must load the integer. That means when we load the integer and we store it in the stack, it's gonna be automatically converted based on the instruction used. So I will show you a couple of examples in here. Okay, if an instruction has two operands, keep this in mind, one of them must be a register, FPU register, must be. So it's like very much similar to the integer, because it's x86 is what? Is a CISC architecture, right? And it is register memory. So we need to have a register in there, okay? So this is very strict. And the destination always gonna be a register. Keep that in mind, okay? So your destination always must be a register. All right, so the operation cannot happen. So this is allowed when we do it in the integer, memory 1 and EAX. So this destination can be a memory. This is not allowed in FPU, okay? So this is something that you need to keep in mind. All right, and now we know the instructions. So the first thing that we need to look at is the data types. So we know the quad word, the T byte, we already covered these in addition to the D word. Remember that, and we have word, right? And we have learned bytes, and we covered them both, and we can also have sign. Okay, so it's gonna be integer or signed integers, right? So here we're gonna have real 4, real 8, and real 10. So this is 32-bit. This is 64-bit, and this is 80-bit, okay? So these are the data type that we're gonna be using in the floating point unit. All right, so now we know the fundamental, the postfix way of working, and we know the stacks, and we know how the stack is gonna be accessed, right? Through the ST0, that's the top of the stack, and we know we have 8 registers, R0 to R8, and we know their size is 80-bit. And we know, like, these are the basic fundamentals, and then we know the basic instructions as well. Now we're gonna go ahead and do some very interesting operations, right? We're gonna write some programs. So the first thing that you need to keep in mind before you wanna do anything, right? You have to load things from memory to register. Remember that? We have load and we have store. If you remember when we talked about it in the beginning, we say load, and we say what? Store. So we say load when we take from memory to register. We use store when we take from register to memory. Keep that in mind. So now we're focusing on getting something from memory, and we want to store it in the top of the stack, right? So these are the instructions. So you can handle 32-bit, floating point, 64, 80, or you may be loaded to a specific register, okay? So let's look at a very simple example right here. So we have a real 8. So now we know real 8, right? That's 64, right, guys? It's going to be a 64-bit. Okay? So this is 64-bit. And this is the value that we have in the memory. So this value already in this memory, right? So you have this memory right here, which is double 1, right? And inside this memory, you have this value stored there, right? Which is 234.56. So the value is stored right there. And then the next value, which is double 2, right? And you have the other value, which is 10.1. Okay, and then now you want to load this into the stack, right? So remember, this is my stack. If you imagine that this is your stack right here, and you know the top of the stack is always pointed at by the ST0. So if you say right here, if load this value, so it's going to automatically load it to the top of the stack. So that's the ST0. So the ST0 right now is going to have what? Is going to have the 234.56. So that's the top of the stack here. Okay, and then we're going to say load 2, load 10.1. So this is automatically, okay, this is automatically going to do what? Is going to increment or decrement. Remember when we load? Okay, so when we load is kind of what? Pushing, right? So we're going to decrement. Right? So we're going to decrement, but we don't care whether ST0 is pointing at R0, R1, or R2, or R5. We don't care. So all we care about is the top of the stack. Okay, so the top of the stack could be now pointing at whatever. Okay, So if this is the case right here, this is now the top of the stack. If we load the second value, then the top of the stack is what? Is 10. Do you see it? So ST0 is the top of the stack. So the top of the stack is something different. And the previous top of the stack is going to be now pointed at by ST1. You see it, guys? So this is how we use float. All right, keep that in mind. We can also say fstore, right? So store when we take from the stack and we need to store it into the memory. So these are the things that you can do as well. So there is a very interesting case in here. So we assume that the ST0 equals to whatever the value is. So this is if we're going to look at this example right here. So right now we say fstore double 3, right? So when we say fstore, what is my source? Okay, if we say float, if you remember, we said float double 1, right? So where is my destination? This is my source. Where is my destination is ST0. Remember that? So right here we said, and that is going to be my destination, right? So that is my source, and this is my destination. This is source, and this is destination. Right here we're using the store. So this is, we say store this. What is my destination is the top of the stack. So that FST, it knows that it needs to store this from the memory to the top of the stack, which is the destination. So it is implicit in there. It's not explicit. I'm talking about the destination here. Okay. So first, what we're going to do, we're going to say store this value, right, which is add 3. Okay. So just say like the double 3. I'm sorry. That's what you have in the double 3. So we assume that this is the value in here. So the ST0 is going to be 10, right? You with me, guys? And this is the top of the stack, remember. So is the top of the stack the source or the destination? So here, if you look at the load, we said load this. So my destination is this, and this is my source. And when we say fstore, this is a little bit confusing. This is your destination. So where is your source? The source is the stack. So keep that in mind. So you are given a destination, and the source is what? Is assumed, is implicitly assumed. Okay, so we're gonna copy the top of the stack, which is this, and then we're gonna take this top of the stack to this memory. Okay, so just imagine if that is the memory, and that is double 3. I'm just gonna for short. So we're gonna copy 10.1 right here. Okay, so that is my ST0. And then we went to the second part and we say, take the second value, which is ST1, and store it where? And store it in another memory, which is what in here? It's D4, right? So we're going to copy this. But after we do this, we're going to see like both of them, they have 10.1, 10.1. And that's very interesting. Okay, we are expecting to see this value here, to copy this one here. But FST is just going to copy, but it's not going to pop. That means when it copies, it's not going to increment. Okay, so it assumes you only want to copy one value, but in this case, we want to copy 2 values. If we want to copy 2 values, then FST is not the instruction we should use. So what should we do? We're going to use FSTB. So FSTP right here, it is going to first copy this. Okay, I'm sorry. It's going to copy this to the memory, right, which is D3. So we're going to have 10.1. And after it copies this, is going to increment. So now the ST0 is pointing here. So when we say FSTP now, it's going to copy what? It's going to copy here. If this is D4, we're going to have 234.56. Okay? And after it does this, since this is the P, it's going to automatically increment. So ST0 is going to point right here, whatever the value is. So keep that in mind. If you want to store 2 values, then FST is not going to help. You need FSTP. All right? So these are now, hopefully, things are getting clear and better in your mind. So now we're going to look at the arithmetic instructions. All right? We know how to load. So we are loading for a reason. We need to call the ALU, add, subtract. Okay? So we're going to look at those basic instructions like the addition, the subtraction, the multiplication, the division. So 2 unique instructions right here, which is this, the subtraction and the division, the opposite of the subtraction. You can subtract source from destination, or you can subtract destination from source. In some situations when you deal with the floating point, you might need to subtract the situation, the destination from the source, not the other way around. So if you want to do it, you're going to use this part in here. I'm not going to use it in this class, especially in the, covering this in this slide is not the focus, but we're just going to first learn what the rule is. So this is just the exception. But these are the instructions that we have to learn. Remember, what is the equivalent of changing sign in the integer unit? Remember that? Can you think about it? How do we flip, right? When we remember when we learned the move SX and the move ZX instruction. Okay, so we also learned with what? We learned how to flip the sign. So that is going to be very important. Okay, so the same in here for the real point or the real floating point numbers. We're going to use this for converting the numbers. Okay, converting the number sign from positive to negative to or negative to positive. Okay, so these are the main instructions. And I will spend the time explaining add, and whatever applies to add applies to sub, divide, and multiply as well. Okay, so the basic idea right here, you can use add with no operand, like the one right here. So where are the operands? You have to load them. So if you have a memory, you're going to say load, right? So now we know fload, right? FLD. We say memory 1. And FLD, we say memory 2. So if I have my stack, and this is my ST0, right? So this is going to be M1 first. And then when we load it, now the ST0 is going to be point here. So this is M2. Okay, so the ST0 now, that's the top of the stack now. Once we load them, then we're just going to say FAdd. So the ALU already, the ALU, the arithmetic logic unit, already knows where those values are. It already knows that they already on the top of the stack. So just the ALU gonna go there, copy them inside the ALU, do the operation, and push the result in the top of the stack. Okay, we're gonna look at a couple of examples, all right? So this is exactly something you can do. You can also add a 32-bit, you can add a 64 with like either no operand, one operand, or two operands right here. And if we use two operands, this is always going to be the destination. Keep that in mind. Okay? So this is the case then. In this case, we say FAdd. So if we say FAdd, this is before, keep that in mind. We assume you already pushed to a value. So that's what I explained right here. So you already loaded. You use this float. You have to do them as a user. So this is, it forces the programmers to load the values first and then call the add. Okay, and this is going to come handy when we're going to handle the postfix, right? This is the way the floating point works in x86 system. All right, so this is before. After we call the FAdd, when we load these two instructions, and then we call this. So now we're going to see the top of the stack is going to be 244.66. You see what I'm talking about? Okay, so this is going to be the result. So it's going to be added, and automatically the result is going to be the top of the stack. Keep that in mind, automatically. And the destination is always must be what? An FPU register. Keep that in mind. Okay? So if we want to do FAdd and we have one operand, okay? If we want to do that, then this is what you're going to look at. We're going to say you have register operands. So if you have register operands right here, ST0 and ST1, so this is going to be my destination. So if you're going to say add ST0 to ST1, so ST1 value should be changed, right? This is when we have a register operands, okay? This is the one that we have right here. So we're going to add this to this. So that's what you see. The result now changed, right? This is not similar to this, right? So it's going to add ST0 to ST1, but it's not going to change anything. The top of the stack is still 10. All right, so this is when you're going to deal with the registers. And by the way, you can add it to any register. It doesn't have to be the top of the stack. Okay, you can add the top of the stack to any register or any register to any register. Just keep that in mind. Okay, so this is when you have a memory operand. So these are the memory operands. So we cover this when we have no operands, and then we cover this when we have registers. So this is the memory operand. So if you have the memory operand, keep this rule in mind, okay? So the destination must be what? Must be FPU register. So when you say F add memory, right? So you already have a memory. Just imagine you have a memory, and this memory points at a value 5.1, let's say. So that is my single. That is the memory here that points, let's say, at this value. So when you say F add, the destination automatically is going to be assumed what? ST0. So it's like this expression. If you have taken C language, you know this expression in there. So it's going to take the memory and add the memory to the top of the stack, and then it's going to update the value in the top of the stack. Clear? So this is basically what fadd is all about. The same applies to the sub. All right, so I'm not going to spend the time on the sub, but I'm just going to remind you, again, it's no operand. This is like the F sub in here, okay? Or you can also handle the, when you have a memory operand or when you have a register operands. Okay, so right here, it's a memory operand. You're just going to say F sub, and you give it the memory, or you're going to F sub, and then you know what type of memory access is this, right? So this is the index, if you still remember. So it's just going to take the index of this memory. If EDI is a 1, you multiply 8 by 1. That means the second element, if it's a D word memory, right? Then it's going to take that value and add this to the ST0. Okay? And this is the fmul, which is very interesting. Again, fmul also doesn't take any value. If you wonder why this 6 is, this is just in the book. If you refer to the book, you'll find a description of what fmul does, okay? So this is just for describing more details in the book, all right? So the fmul right here, it's the same. If you say fmul and you give the memory, so the multiplier, if you remember the multiplicand and the multiplier, so this is going to be your multiplier, and the multiplicand is going to be the top of the stack. So your multiplicand must be loaded first to the ST0. Okay? So let's look at this expression. All right, so this is the example that we're going to look at right now. So let's say if we want to use those instructions that we learned so far, just to apply those to solve this expression. Okay, so let's do it together. So what we need to do first. All right, so the data are 32-bit. If it's 32-bit, then we need to declare what? Real, right? Real what? Real 4, right? So we're going to have real 4 of what? What is it that's real 4? It's A, right? So A is going to be real 4, and it's going to be 1.9. And B, it's going to be what? Real 4, and then it's going to be 2.1. Okay? And then we know we cannot have C in x86, right? Because it's a keyword. So we're just going to say C1, real 4, and then this is going to be 5.3. And then we're going to have D, real 4, and then this is going to be 0.3. And then we're going to have E, real 4, and this is something that we need to figure out, right? That's the expression, the last value of the expression. So we know it's postfix, right? So we can do it in multiple ways, all right? So the way I would like you to focus on is to use 0 operands, because that's going to force you to think mainly on postfix. So 0 operands, we just want to load the values, and then we're going to call the ALU. So we know data first. So we have to say first in here once we did this. I'm sorry. Let me see. So once we do this, we just going to say float, because it's memory, right? We're going to say float what? A. And then we're going to say float what? B. And then we're going to call what? Fadd. Okay? So fadd, if you look at this in your mind, if you think about it, so this is the ST0. It points at the top of the stack. It's going to be A, and then the top of the stack is going to be B. Okay? And then we're going to add B to A, and then the result here is going to be added back to the top of the stack. So the top of the stack is going to have the result 1 value. Okay? And then now what we need to do, we're just going to say float, just no operand, this one, right? We are not going to use any operands. So we just load, and call the ALU. So you're going to say float is C1, and then float D, right, guys? And then we're going to do what? Let's see if I can do it here. And then we're going to do what? We're going to say F sub. Okay, so when we load this, then the top of the stack is going to load what? Is going to load C, and then the top of the stack is going to be what? is going to be D, right? And then it's going to subtract this from this, and then the top of the stack now is going to be the subtraction, right? So the top of the stack is going to be the subtraction, okay? The subtraction of these. All right, so if you look at it, when you do the F sub right now, if you look at the stack, I will see if I have the time to show you that in Visual Studio. Otherwise, you will do that in the lab. So now the ST0 has the C minus D, and ST1, and ST1 has A plus B. So these are the the binary values that we have in the top of the stack. So now we are ready to call what? Mul. So if we're just gonna say F mul. Okay, so all we do is just gonna say F mul. So F mul is gonna multiply this by this and put the result on the top of the stack. So the top of the stack is gonna have the result. Once we do this, we wanna store the data back on E, right? So we're just gonna say F ST. Do you need P? Because you're storing one value, you don't need it, but if you want to write it, that's fine. So you're going to say FST into E. Okay, so you're going to take the result from the top of the stack, and then you're going to store it in E, which is we already declared right here. You see the idea, guys? Okay, so hopefully now you understand how you declare the data type, how to apply the load, the fadd without operation. And in the lab, you will see that I provide you with an example where you're going to do you can do this in a different way. You can say it in this way, as you will see it in the lab. You can say F load A, and then you're going to say F add B. So this way, this F add, it is of what? It has two. It has one operand in this case, which is the memory. I'm sorry, it's not clear right here. Let me see if I can write it better. This is going to be, go away. This is going to be F add, go away again. It's going to be F add what? D. So it knows that it's going to add D to the top of the stack, which is what? Already A. So this is another way to do it. You can do it in another way as well. So you can F load both right here, like what we have right here, right? And then after that, you're just going to do what? You're just going to say F add ST0 ST1. You see it? You can do that as well. So the reason I said stick with the no operands, because it's very important for you first to think about data operation, then data operation, and so on and so forth. Okay? The dev is exactly the same. So you just, whatever we said, we learned so far in add and subtract applies to the dev. There is nothing new. You just need to load, and do you see it in here? So when we load, we are saying we load one value and then we divide. So this is one operand. So this value is already on the ST0. You with me, guys? And then when we say divide, so the destination is always the ST0. We're going to divide this by this, and the result is going to go to the ST0. This is what you can see in this part. So the fdev is like add and subtract, exactly the same. It's either no operand, or it's going to be memory, or it's going to be registers. Okay? So the one thing that you need to keep in mind when you say fmul and fdev, the no operand, this is the no operand, is always going to automatically pop the top of the stack. So this is very important to keep in mind. So if you say fmul, no operand, so it's going to pop the top of the stack automatically. But if you say fmul or fdev and you say b or a, it's just going to do the multiplication, but it's not going to pop the top of the stack. So you have to do the pop if you need to access the next value. Okay? So this is exactly what we did in here. So we have the two variables. We declare them. This is 10, and this is 1,000. And we divide this by 10. And the result already on the top of the stack. And we store now the result from the top of the stack where? To the memory space that we have right here. Okay, which is the double quotation that we have right here. Okay? All right, let me see. So this is a very interesting example, another example. So here we have single operation, right? This is not a binary operation. This is a negator, right? It's like negate. Remember negate in x86? When we use it, negate, EAX, it's going to negate the value. So this is negation. But we know we have equivalent negation instruction in the floating point system, right? So if you go right here, first we want to load A, right? You have multiple ways to solve this problem, right? Either no operands or one operand or two operands. It depends. So in the exam or in the lab, if I say use one operand, then use one operand. Use no operands, then use no operand. Okay? So right here, what we're going to do, these are my values. I have value A and then value B, value C. These are the ones that you see right here. And then value D, that is when we're going to store the data. So first here, we load value A, and then we change. Okay, so it has no operand in here because it knows the top of the stack is going to go there and it's going to negate. So if it's positive, it's going to become negative. If it's negative, it's going to become positive. Okay? And then now we are loading what? We are loading B, right? And then we are multiplying what? C. So we loaded this to the top of the stack. Let me see. So let me see right here if this is my stack. So this is the ST0. And then in this ST0, we have A, we negated it, right? And then the top of the stack now points here, right? So the top of the stack now is going to be what? B. And then the top of the stack again, it is going to be what? It is going to be what? Here. So we loaded B, that's the top of the stack, and we're going to say F mul what? Value C. Did we load it value C right here? No, that's going to be in the memory, right? Right, guys? So it's going to take this value from the memory, multiply it with the top of the stack, which is B, and the result is going to remain right there in the B part. Okay? So that is going to be the result in the top. If the result is already on the top, so the expression right here, the result now is the top of the stack. So the top of the stack right here is B multiplied by what? By C. That's the top of the stack. Okay, and then now we're going to say add. So we know A is still there, which is A right now is going to be what? Is going to be ST1, right? And the ST0 already B by C, right? If that is the case, add, we have no operand in here, right? So it's going to take this top of the stack and add ST1 to it, and it's going to pop because it has no operand. It's going to top automatically the top of the stack with the new value. Okay, so the new value is going to go to the top of the stack. So ST0 now here is going to have a new value, right? The new value. That's going to be the top of the stack. Okay, so if the top of the stack is the new value, which is the result, we're going to copy that value to where? To the D location. Okay, so you're going to see the instruction right here. Change, load B, and then now we're going to multiply C with the top of the stack, which is B. That's what I said right here, B. And then now we're going to add ST1, which is A, the one we loaded in the beginning. And then we're going to add it to the top of the stack. Then the result's going to be in the top of the stack automatically because you have no operand. And then now we're going to store the top of the stack and the value on the memory D, or the D memory. Okay, guys? So far, so good. Okay, you maybe sometimes have mixed mode arithmetic. So mixed mode means you're going to have integer and you're going to have floating point. So how are you going to deal with that problem? Okay, so if you have integer, you cannot use add or mul to handle them. Okay, and the FBU instructions cannot actually deals with the integer, right? So we need to figure out a way to convert the integers, right? So the best way to do it is to load the integers, either 62-bit, either 16-bit, 32-bit, or 64-bit. Okay, so you need to store them using this instruction. Remember, the second character is going to tell you about the type. So floating point, integer load. So you're loading integer. Okay, here you are what? You are storing integer, right? So storing, you're taking them from the register back to the memory, or you take them from the memory back to into the register. Okay, so when you do this conversion, it's going to be 80-bit automatically because the size of the register or the registers are 80-bit already. Okay, guys? Or if you don't need to do it in this way, you can also use any of the fadd, sub, or mul, but you're gonna just do it for what? For integers. Okay, so they're gonna automatically convert the integer, those instructions here and those instructions there. Okay? Excuse me. So let's look at this example. So if you have this expression right here, and we want to add n to x. And remember, n is an SD word, right? So these are 4 bytes signed integer, okay, positive or negative. And then we have real 8, which is 64-bit, right? And then we have z, which is 64-bit. All right, so we need to handle n. So the best way to do it, just fi, load integer, right? So we load n integer. If we load it, then it's going to be automatically what? 80-bit. Okay, so it's going to be an 80-bit. So the top of the register right now is going to be an 80-bit converted integer. All right, and we say wait. Why we say wait? We wait for exception. Why? Because sometimes when you convert, the CPU might crash for some reason, because of the rounding problem, because of the space problem, the capacity. So we have to wait. You don't have to. It's safe to say wait. In case of an exception happen, you can capture it and you will know what's going on. But you don't have to do it, okay? This is just for the safety. And then once we do this, we know the top of the stack is there. So we're gonna say add what? X. So this is what? This is an add with one operand and it's memory. So it's gonna add this memory to what? To the ST0. So the top of the stack now, it's gonna be the added value. Remember, when we use an argument with the add, mul, dev, subtract, all of them, when we do that, the top of the stack is gonna be there. It's not gonna be popped automatically. So the top of the stack has the result, okay, but it's not gonna pop it. Keep that in mind, okay? So right there, if this is the top of the stack, the result in the ST0, so we're just gonna copy the result from the top of the stack, and we're gonna store it where? We're gonna store it on this Z. Okay, guys? So this is basically the basic idea of dealing with the floating point unit. Okay, so if you don't mind, I just want to go here and try to show you like a very quick example of what's going on. Let me see if I can do that. So I'm supposed to go here. Hopefully you'll see the Visual Studio right here. Okay, so right here, what we want to do, let's just declare a variable right here. Okay, let's just say C1 is real 4, and let's say 1.5, and let's say B is real 4. That means 32-bit, right, guys? And then it's going to be 1.5, and let's say we have D, and it's real 4, and let's say we're gonna say question mark because we're just gonna store the data. So we're just gonna use no operand. So we're just gonna say FLD, what? C1, and then FLD, and then we're gonna say B, and then we're gonna say what? FAdd, right? So this is what we have in mind. All right, so we are very used to integer registers, x86, EAX, EBX, ECX, and the E flag and everything, right? Now you will see something different. You will see those steps in the lab as well. You will play with them in on the next lab. But let me see right now if I can run this. Let me create the breakpoint right here. And let me run the program. Hopefully we don't have a problem. Okay, it seems we don't. So the one thing that I want you to keep in mind, these are the things that you will be doing in the lab. Okay, but I will just bring your attention to those. So we don't need those. We don't need the integer registers anymore. We need the floating point registers. If we want to do this, we're just going to right click in here. And if you notice right here, we're going to say the floating point. I don't know whether you can see it or not. Okay, so if we say the floating point, then we should be able to see the ST0 and ST1. Do you see what I'm talking about? So this is ST0, this is ST1, this is ST2, and so on and so forth. And if you go to the bottom, you will see all the E flag for the floating point, the overflow, the sign flag, the zero flag, and everything. Okay? So this is going to be something that you will play with in the lab. All right? So now we're no longer dealing with the integer. We need to go right here. So that's the top of the stack, right? Let's see if we load C1, which is 1.5, it should go to the top of the stack, right? So if we do this right here, okay? So this is going to be the instruction pointer now moves. So that's the top of the stack, 1.5. Okay? So now if we load B, then the top of the stack, ST0 should be 1.5, right? And this 1.5 should go to the ST1, right? I wish I had it 1.4, so that way you will see the effect very clearly. Okay, so the instruction point now, pointer points at the next instruction. So this is the top of the stack is 1.5. So we say fadd. So fadd is going to take, it's going to take right here the ST1, if you see the pointer right here, and it's going to add it to ST0, and it's going to pop the results. So the 3 should be seen here at the ST0. You see what I'm talking about? So if we want to do this, we're just going to go right here. And now let's go and look at the floating point. And then you will see now the top of the stack, I'm sorry, is 3. And since it tops the top of the stack, so whatever value you have in ST1 is going to be overwritten by a 0. Okay? So I hope that that's very clear. And if you want to look at the memory here, the real memory, because what you see here is binary, right? So if we want to go to the C1, you know what you guys need to do, right? So just you're going to say the ampersand C1. So we're going to go and look at the value, but this is not the way we want to see them. So we're just going to say right click, and we need to go and look at the floating point 32-bit. Do you see it? So this is floating point 32-bit. So this is 1.5, this is 1.5, and the next is going to be the result. Okay, so now when we did the addition, is the result going to go back to D? No, because we don't have the store. So we need to add the store after the fadd. You will do that in the lab, but I'm just trying to show what we've been covering so far. The theory part, it has the implementation or the application part, and you're going to do that in the lab anyway. Okay, so if I can go back now to the slides and go back to share the slides. Okay, and I just want to wrap it up in there by covering these two topics. So now I hope you're clear in your mind. So what we mean by a floating point, how to do the rounding, what's the floating point exceptions, and the instruction set, the arithmetic instructions, and the mix operation. So the only two topics right here, we're going to cover them very quick, which is if statement. We already covered that in more details. It took us 2 weeks to cover that, right? An integer. It's not going to take us so long in here because it's straightforward, it's handy. And then we're going to see how to read and write floating point values, okay? And these are very important for your next lab. All right, so let me see right here. So in the floating point, if we want to compare two values, we know in the integer unit, if we want to compare, right, we're just going to say move, remember that, to AL, let's say 5. And then we're just going to say compare AL with let's say 6, right? So if I'm making an F statement, right, guys, we use F statements when we do the compare, and then we're just going to have the jump instruction, jump if it's above or jump if it's below, it depends. So we covered all of that. So we know compare is nothing but subtraction, right, guys? An x86 integer unit, right? The same applies for the floating point. So whatever we learned in these like past weeks, they're gonna come handy right here. So if you want to say compare, F compare, so it's gonna compare S0, ST0 with ST1, and you know how the comparison happens, right? It's by subtraction. And why we subtract? Because we want to affect the E flag. It took us 2 weeks to learn, right? Hopefully that is there. If not, please go back and try to revise the material in there. Okay, so you can compare registers right here. You can compare register with memory. You can compare with memory 32, 64, or you can compare registers, the top of the stack, which is the ST0 with any of the registers. It doesn't have to be S1, ST1. Okay, so this is like the basic idea. And we know in the integer register, when we subtract, when we say compare is subtract, we compare AL, which has a 5 with 6, right? So we're going to subtract 5 from 6, and the result is going to be -1. So the sign flag is going to be what? The sign flag is going to be raised, right? And based on that, the jump instruction, the J instruction, is going to decide whether, if this is, if you remember, above and below for unsigned integer, and greater and less than is for the signed integer. Since we are comparing signed integer here because we decided G, jump when it's greater. So this is greater than that. Okay, so we just want to make the decision. Since the sign flag is raised, we know it's not greater. It's not a greater, and then we are not going to decide. We are not going to jump, right? So here, the same thing. We have a different thing. We call it condition codes. The same thing in terms of the E flag. We need to capture a value. All right, but it's been set up in a different way. So the 0 flag, we call it condition code C3, C2, and C1. So this stands for the carry flag. This is for the parity and the 0 flag. So I know you use this for quite some time, so I'm not worried very much about it. You've been tested, you've been playing with it in the lab. You did that in your project assignment as well. So this is basically what we need to do. If those condition codes are all zeros, then we know that ST0 is greater than the source. Okay, so that's how the jump is going to work, right? Jump when it's above. And we know this is equivalent, right? Jump when not below. All right, so if all the flags are 0 except for the carry flag, then we know that the top of the stack is less than the source. All right, and if the carry of the 0 flag is 1, then we know that both of them are the same. Remember that when you subtract 5 from 5, then the result's going to be 0, then the 0 flag is going to be set. Then we know that these are equal, not greater, not less than. Okay, and if all of them are set for some reason, then this is an exception. Something wrong. It's like beyond what the FP unit can handle for some reason. So if that happens, if you have all of them once, then there is an error, and maybe on your data, maybe on the way you compare, maybe on the range of the data. So we need to just figure it out. So this is a basic example in C. So you have X and Y in here, and you have an integer n equal to 0, and then you need to compare what? X with Y, whether X less than Y. So we declare it here. Since this is double, we know double in C or in Java is going to be 64 bits. So that's why we used real 8, not real 4, and we assign the values. So this is mainly an assembly, and this is our do word, which is the integer. And here we want to convert this expression, right? Mainly the F statement. So we're going to load X first, okay? And this is a little bit long story. We will simplify it. This is old x86. This is how the old x86 works, okay? So how they work is they're going to compare Y with X. We know when we compare Y with X, we're going to subtract Y from X, right? And when we do the subtraction from there, we're going to affect the E flag. Remember that? And if you're going to affect the E flag, then this is what you need to do. First, when you do the subtraction, the floating point unit, it captures the condition code. So that's the S0, S1, sorry, C0, C1, C2, C3, and so on and so forth until C7. Okay? And we're going to go for 32 bits. So what we need to do, if you just imagine, because this is like really shows you a weakness of an architecture, the x86 architecture. So the real comparison doesn't happen inside the FPU. It actually happens inside the integer. Though it's a floating point number, it's very complex, okay? But what happens there when we do the subtraction in here, this is gonna be my EAX 16-bit. So we copy this, why? Because these has the flags that we care about the most, C0 to C3. So we copy all of them, and then once we copy all of them using this instruction, then we copy just the first 8 bits. And remember, this is the AL and this is the AH. We're just gonna copy the AL because it exactly has those values. We copy them in there, and then we're gonna call the what? The jump, the integer jump. So the floating point doesn't really have an real F floating point processing unit, okay, when it comes to the F statement. All right, so this is how it happens. And then it's say jump when it's not below. And this is exactly what we did before, right? Jump when it's not below. All right, we know we have to negate. Remember, if we don't negate, it's going to be very complex. I know it's below, not below. It's going to be greater than. If it's greater than, then do not do anything. Do not get to the F statement. It's false. Get out. Okay? If this is true, we execute this. If it's false, then we're going to get out. So if this is false, get out. If it's not, then move 1 to N. We already covered that, right? When we jump, when we not jump, and when we convert, when we do not convert, right? Using the demarking law. All right? So if that is the case, and starting Pentium 6, they change FCOM into FCOM-I. So in the FCOM-I, you're just going to compare the top of the stack with ST1, and then you're going to make the decision. So the whole idea is they take off these 2 instructions because they are very confused to the programmers. So they said move them and replace them with this instruction. The cost was that you no longer are allowed to use memory. So if you have memory to memory, you have to load both of them into the stack, and then you start comparing them after that. This is a basic example right here. So you have 2 memory in here, and then you need to compare them. So load this, and FCOM-I ST0 with ST1, and jump if it's above. Okay, so this is straightforward type of comparison using the floating point unit. The last topic right here, it's going to be mainly reading data. So if you want to read data, remember, if we deal with the procedures or external libraries, we have to include our Vine32. We're going to use this macro right here, and this macro requires including macros inc. Okay, so you need to include this in the lab when you're playing with this, otherwise you're going to get an error. So this is, we read a floating point, we write a floating point, we present the status of the stack with using this instruction, displaying it, and with this one, we're just going to write the content or a message, a string. Remember, we have a similar write string in the integer unit, right? This is a little bit different, but you can use it if you want, by the way. Okay, so so if you have this example right here, and you have 2 values right here, and this is like the result where you need your result to be there. So you load first, and then you load second, and then you called what? Show the stack. So when you say show the stack, it's going to show you the top of the stack and the rest. It's going to print it out on the screen. Since you loaded both values, you're going to see the details in there. Okay, and this is the product as well. So whatever the content of the register, you're going to see them printed out on the screen instead of seeing them inside the Visual Studio window in there. Okay, so let me go back. And then after that, you're writing a message. Say, please enter a real number. So you can do that as well, and you're going to read a number. So if you read a number, that's going to be the top of the stack. So the ST0 is going to point at that number, whatever that number is. And then you're going to enter the second number. So you're going to read. So now the top of the stack is pointing at the next. So this is going to be ST1, and this is now is going to be ST0. That's the top of the stack. Okay, and then now you're saying fmul, and you're using what? We have no operands, 1 operand, or 2 operands, right? So this is 2 operands. So you're multiplying ST1 with ST0, and the result is going to be an ST0. Okay, so here you're using this macro. You're going to say their product is, and then you're calling what? Write float. So the write float is going to go to the top of the stack. It's going to find the result of the multiplication, and then it's going to print that on the, into the screen. Okay, clear the screen and come to the beginning of the line, and we're going to end the code or end the program. Okay. So this is basically what the floating point is, and this is what I explained right now. And it's been a very interesting couple of weeks learning the floating point. And now I hope that you guys understand the relationship between the software and the CPU. And you as a programmer right here, you need to understand both. So hopefully now with the help of the assembly language, we were able to really see how the software interacts with the hardware, because this is really hard to see when you are using a high-level language like Java. So now if you see integer A in Java, hopefully you know what integer is, what A is. This is all in your mind. You say, oh, this is a space, 32-bit. Oh, this is a location, okay? And oh, there is an E flag. Maybe when we add A to another B, there is a capacity. And if we exceeded, the E flag is gonna be raised, and so on and so forth. So hopefully what we covered so far helps you as a helps your programming understanding and how software interacts with the hardware. So as I always say, if you are around this part, you're really good. If you are here, it's good too. But if you are around here, let me know, please. I have my office hours. Just stop by and I'll try my best to help. All right. So goodbye for now and talk to you later. Thank you, guys.